Okay, in the previous lesson, yesterday, we have seen how many errors we can have in the GPS observation and how we can deal with this error to correct the effect and obtain a precise positioning. Okay, now we are going to see better the techniques that you can use to do this. To reduce the errors in GPS observation, you have principally two approaches: relative positioning or combination of observation. As for the ionosphere free observation, L3, as well as we have seen yesterday to reduce the ionosphere effect. Of course, these two approaches can be mixed. We can compute, for instance, L3 combination, iono-free combination, and use this observation in relative positioning. So, to be honest, we use a mixed technique. So we mix these two approaches. So we started from relative positioning. It means that we don't use just one single receiver, but we connect a receiver in the processing. It's not a physical connection. We take measurement by one receiver and by another receiver, and we can compute some differences of the observation. In this case, all the common error present in the data can be removed if you use differencing. So, before we start, we say that given two receivers in the benchmark A and the benchmark B, the vector connected these two vertices are called baseline. Okay, so now we are going to speak about baseline, about this vector, the connection of two receivers. Okay, when we have different type of differences, is different order. We can speak about single differences, double differences, or triple differences, and we are going to see. And this observation differences can be performed for using pseudo-range observations, that mean code observation, or phase observation. So, single differences between receivers. So, we have two receivers, A and B, that at a given moment are observing the same satellite. In the figure, we have satellite number 1. And if you, in this case, if you take the phase observation, you can compute the differences. This I don't put as a variable the time, but now we are speaking about a fixed epoch. So we compute the differences between observation at the same time, are synchronized. So we have a phase A from the satellite 1 at time t0 minus phase B, phase in the receiver B with respect to satellite 1 at the same time t0. Okay, and if you write the expression of the equation of the phase, we can see that we have a term that where we have our geometric unknown parameter, the coordinates of the two receivers, A and B. We have the clock of the error due to the clock, the ambiguity, and the ionosphere-troposphere effect. So, in this case, you can see we can cancel some term. One term that you cancel in an easy way are the term due to the error of the satellite clock. Okay, it's not a big term because we know that clock of the satellite are really synchronized with the GPS term and are synchronized between satellites. But in this case, this is the same term, and we can reduce for this. But we can reduce also for these two terms, ionosphere and troposphere delay, but at one condition: if the baseline, the distance between A and B, the two receivers, is shorter than 30 kilometers. In this, under this condition, we can suppose that the atmosphere is more or less the same at the two stations. So we just in this if this condition is respected, we can cancel this effect. We can also cancel orbital error. In this equation, we didn't write the orbit error, but if you put a term related to a frequency, a term like delta E, this term that takes into account for the orbit position error is the same. We are looking for the same satellite, so it's the same error, and also this is being cancelled. Okay. So with single differences between receiver, we can remove this type of error. Oh, this is an old remark. The error in the knowledge of the length of the baseline is correlated to the error in the distance between receiver and satellite. And this is the relationship. So with a shorter baseline, we have also a shorter error in the position due to the position of the satellite. Okay, this it's an old slide. It means that in the past, when we started to have precise ephemerides, we take a lot of attention on this problem. So we try to use shorter baseline. Now I think that we try to use shorter baseline distance between points because we want to reduce atmospheric problem, not for the orbit problem, because now we have very good orbit information, precise ephemerides. Okay. We can also compute single differences between satellites. So we take just one receiver and we take into account for the observation coming from two satellites at the same time. I don't put the time, but it is in all the slides we consider a fixed epoch, a fixed time. In this case, we can just remove the receiver clock error. You can see in this equation the only term that we can cancel is the receiver clock error. But we know that the receiver clock error is a quite big error. In fact, we are going to estimate this one. So it's a good difference, it's important. Okay, now we have seen that we can compute single differences between receiver. You have to, you can see the symbols that I'm going to use. Okay. For differences between receiver, I use these symbols, delta. Okay, that is like a triangle that we can make between the two receiver and the satellite, just to remember. With single differences between the satellite, we have the opposite triangle. Okay. And we can compute double differences. It means the differences between two single differences between two receivers. So we have receiver A and receiver B and satellite 1. And we compute these single differences between receivers. And if these receivers are observing simultaneously the same satellite, satellite 2, we can also compute the single differences between receivers with respect to the satellite. And computing the differences of this observation, I don't put all the term, but you can just check using the previous equation. You see that the only terms that we have are the geometric term. D means the distance between satellite and receiver. So it's a part where we have our geometric unknown parameters, the coordinates of the point A and B. And we have a combination of initial ambiguity. So we have removed receiver clock error, satellite clock error, atmospheric error if the baseline, again, is shorter than 30 kilometers, more or less, of course. It's an approximation. But if this point are if the distance is shorter than 30 kilometers, we can remove the atmospheric effect. So the double differences is one of the most used observable used in the GPS processing software. Is a base. The software uses to resolve the equation and to estimate all the parameters that we have seen. We use this observation. Of course, often we have a longer baseline, so we have to introduce also the term due to the atmospheric error. And so we use this observation to estimate coordinates, ambiguity, zenith delay due to the troposphere, and so on. This is the common observation that precipitation delay. Okay. Okay, we are going to see that when you compute differences, we are going to amplify the noise present in the data. We have measured with some error. Any combination of our measure, we have to take into account for the propagation of the variance and covariance matrix. So also in this case, we are going to see that this combination removes the biases, the common error, but we have a bigger noise, so the signal to noise ratio is bigger, but we remove the bias. Often the more difficult things to deal with in data processing are the biases, not the noise. We can resolve the problem with the noise. But when you have a lot of noise, you can have some problem in the estimation of the parameters. Okay. We are going to see better later this expression. So from the double differences, that means the differences between two single differences between receiver, this expression can be linearized, and we are going to see better later, and we obtain a relationship related to the differences between receiver and differences between the relative position between the two receivers. So it's a relationship equation when we connect. It's important the baseline. It's respect to the baseline. We have information about the baseline of between the two receivers. We are going to see better later. So we have seen that if you consider the covariant matrix of the phase measure given by this simple relationship, so sigma square values, standard variances multiply for an identity matrix, we can, if you compute the covariance, the propagation of this covariance for double differences, you obtain a covariant matrix of this type. So we have increased the error because at the beginning we have this situation. We have no, sorry. And combining two of these with an identity matrix, we increase the variance outside the matrix and also along the I have to check this. If you really have to here and here is straight. No, yes, it could be, yes. And you also introduce, of course, correlations. So we have not a diagonal matrix. Just it's just to say we can study any combination of observation, but we have to take into account for the noise, because we are going to see that, for instance, the triple differences that we are going to introduce are very important because we can reduce a lot of error, but it became very noisy, this observation. So it's not so easy use for some part of the processing procedure for reducing cycle sleep and so on, but it's too noisy to obtain the estimate of the unknown parameters. So we have to take into account for this aspect. The triple differences, as you can see from the slide, are the differences between two double differences, but at different time, epoch 1 and epoch 2. So A and B are observing satellite 1 and satellite 2, and we mix observation at different time. In this case, of course, we are going to remove the ambiguity, because we know the ambiguity are constant values due to the first distance between satellite and receiver. When you can track signal from a satellite, you introduce this unknown parameter, the ambiguity. But this value is a constant, is related to the epoch when you started to track the satellite. After, you remember, we start to count the integer number of cycle. We measure the fractional part of the phase. We start to count the integer number of cycle of the hour carries, periodic signal, and we don't know how many cycles we had in the distance between satellite and receiver at that time. Okay, so compute the differences between the observation two different time we are going to reduce for this for the ambiguity, and we remove a lot of we have just geometric quantity, but it's very noisy, so it's difficult that we can use this observation to estimate the coordinate x, y, z of a point. Okay, have you got any question about it? It's very easy, just to compute differences between observation. Okay, and the software do this. We don't have to decide, okay, now you have to do this on this. There are some strategies already implemented in the software. You can decide which strategy do you want, but normally it's quite the software are made to do this. Okay, now we are using software that process a lot of data in a batch mode. So you put all the input and you don't really know each steps. But in the past, when we have a smaller network, some software you can use, for instance, Bernice. You can see all the steps. So you start for your receiver, you compute the first solution using the code observation to obtain a priori coordinate if you don't know nothing about the position of this station. We are going to see why we need a priori coordinates, approximate values for the coordinates. And after, you can decide to connect a site with another site and build the double differences and so on. And after, when you have decide the baselines that you want to process, you can start to use triple differences to correct cycle sleep. When all the cycle sleep, or most of them, were fixed, you can start to use again double differences to have the estimation of the coordinates. So if you process data step by step, you can see all this process from the raw data, just the observation from one station, and how we are going to build this type of processing. Computing baseline, connecting point with baseline, and computing differences. You can also see from the script all the sequence of programs that we are going to use in a batch procedure, of course. If you look at any step, you can understand, okay, now in this case we are just computing approximated coordinates. In the other one we are building single differences, and so on. Okay. Okay, we have seen that to reduce or to cancel some error, we can also combine observation. Given one station, we combine observation of this station. We have seen this approach with iono-free combination. That we have seen that in this case we reduce the first order ionospheric delay. But we have also other combination. It depends on what you want to obtain. For instance, there is this geometric free combination. Sometimes you can find different term, different name for this combination. Okay, you have to check in the software. In this case, all geometric and other non-dispersive delay, non-dispersive it means dispersive delay is related to ionosphere, okay? So, the geometry and non-dispersive delay are cancelled, but not multipath ionospheric effect. So this combination can be used to study multipath effect or ionospheric effect, for instance. The GPS data processing usually can give you compute the coordinate of sites, but also the other parameters. The tropospheric, okay, the ionospheric parameter, or the phase center variation parameter, and so on. Usually you can decide what you want to obtain. We have also wide lane linear combination. This is wide lane is used to compute cycle sleep ambiguity. In fact, in this combination, the combination of the ambiguity of this observation give us an integer number, so it's easy because we are going to estimate again an integer number. In other combination we obtain, for instance, in iono-free we don't have an integer number of the ambiguity. And we have also this combination that reduce for a lot of effect, the ionosphere, the geometry, the clock, and the troposphere. So it can be used for other type of estimation, and so on. It depends on what you want to obtain. And this is a plot about the noise that we are going to introduce. If you consider the L1 observation, and we see that we use its noise as a reference noise, we see that with the iono-free combination we increase the noise in our data of 3. And with L5 of a higher value, and so on. And we also have a different wavelength of the signal. So sometimes it's important to use a combination with a long wavelength, because it's easier to repair big cycloslip. It's like if you want to it's a very practical, to give you an example. If you want to repair a hole in your pants, you are going probably to put a big piece of clothes, and after you are going to refine the hole. It's difficult to be very precise with small pieces of clothes to repair a hole. So you use like a first approximation, a long wavelength. So it's easier to repair at the first order a gap in your data. Ionosphere, okay, this is the quantity of ionosphere effect with respect to L1. Of course, the iono-free combination don't have any effect in terms of ionosphere, and so on. It's just some information. Okay, so now we start a part that sometimes I know is not so easy for the student. Why? Because if you come from the surveying field, okay, it could be easy, because you know that from your measure, you have to attain the coordinate of the point of a network, and how these points are connected to each other has an effect in the determination of the coordinates. We are going to see more or less the same thing for the GPS. This is important to understand what is the output of a GPS software. So usually we use relative positioning, especially for geophysical application. We don't use relative positioning, but different type of positioning, differential, and so on, just for surveying application. In geophysical application, we have a network of station, or like in this example, we put 2 receivers across a fault, for instance, one receiver in a hanging wall, one receiver in a footwall, for instance, and we put these 2 receivers and we want to measure the deformation. To reduce all the errors that we have seen and to have a very precise positioning, we are going to use a relative position. So we are going to build the baseline, the vector connecting the 2 points. So that means that this vector will be given by the components of this vector will be the difference between the coordinates. And we are going to see that what we obtain by the GPS data analysis are this quantity. And after we are going to see how from the component of the baseline we can obtain the coordinates. So to obtain the coordinates of a point B, if you measure with the GPS data the baseline using a relative positioning, you have, of course, to know the coordinate of the point A. It's a relative positioning, so I fix the coordinate of a point if I know the coordinate of the other point. So this is important because we are going to see how we fix our coordinates. There are different approaches. Okay, this for 2 stations, but often we have a network of stations with a lot of receivers that are working simultaneously, and they are observing a given number of common satellites. For instance, and a given number of satellites. So we have a lot of observation, because from satellite A, you obtain the observation from all the satellites. From satellite B, the same, C again, and D again. And so we want to compute a relative position. So we have to decide how to combine this station. I can build a baseline between point A and point B, or also between point A and point C, or point A and point D, and the same for the other. Also for the single differences between receiver or between satellite and the double differences, we have a lot of different combinations. So there is some rules that we have to know about this possible combination of our observation. So, from this, for example, for a network of station A, B, C, D, and so on, and satellite 1, 2, 3, 4, and so on, we want to create double differences. But if we have n single differences, the number of linearly independent double differences is given by n minus 1. So we are going to, now we are looking at how we can compute double differences. Starting for single difference. After we are going to see the similar problem with the single differences. So if you have n single differences between, for instance, a receiver, so if you have n baseline, the number of double differences linear independent is given by n minus 1. All the software know this one, and when they don't create all the possible combination, because we have a correlated observation, not correlated. We have a not independent observation. And all the method to estimate parameter are statistical method like least square or Kalman filter, but least square is the most used. And we are going to see that when the problem is the least squared, we have to invert a matrix called normal matrix. And to invert this matrix, you need to have the determinant of this matrix different by 0. Okay? And to respect this condition, we have to use a linear independent observation. Later I see the step with the least square, but it's important that we need linear independent observation. So the software don't create any possible combination. If they could create all these possible combination and check which is the best set, looking for instance the noise to ratio, the signal to noise ratio, for instance. At the beginning I can compute everyone, but when we have to estimate the parameter, we need linear independent observation. So we try to explain. If we have 2 receivers, what happens? We have a simple case, and we see, for instance, for satellite, we know that we can see at least for satellite because the system has been set up to respect this condition that is necessary for real-time positioning. So at the moment we suppose that the 2 receivers are quite close, so we don't introduce atmosphere parameter, just to simplify the problem. So we know that at least we have as unknown the baseline component so the x, y, and z component of the vector AB of the baseline, and the ambiguity, the combination, we are speaking about double differences of the initial ambiguity, the n. We have seen in the double differences equation that we have this type of, in the equation we have a combination of ambiguity. Okay, and it's related to which satellite, which receiver we are using, and which couple or which pair or satellite we are using. So at a given epoch, one just epoch, for instance t tan equal t0, we can write three linear independent equations for the relationship we have seen together before. So, but we have to estimate, we have to estimate 6 parameters. So, we have just 3 linear independent equations. Okay. In fact, we can try to compute this. We have, with the receiver AB, we can compute these double differences using the pair J and K, J and L, and J and B, okay, as a pair of satellite. Okay, but any other combination, so if you take, for instance, another pair of satellites, for instance, LMM, we can see in a very simple way that is given by a combination of the double differences that we have seen in the previous slide. So we have seen that given this situation, to receiver for satellite, the number of independent equations is equal to 3. And the other combination between satellite and receiver are a linear combination of these 3 independent double differences. So we have just 3 observations at the given time, but we have 6 unknown. So to solve the problem, we introduce the observation given to another epoch. So we use a set of observation. In fact, the GPS data analysis is a very redundant problem because we use a huge number of observations. I switch on my receiver at time t0, and the receiver recorded the data, for instance, every 10 seconds. So I have an observation for each receiver, for each satellite, any 10 seconds. And I can use all this observation to compute my positioning, x, y, z. That's what we want for the physical application, for the study of the deformation. So we have redundant observations, so we can use statistical method of estimation, like maximum likelihood estimation or least square estimation. But least square, I think, the most used method. And okay, now we are going, from this lesson we start to speak about least square estimation. Do you know what is a least square estimation? Yes, more or less. Probably you have used this for a very simple case. I'm a physicist. In Italy, we know that we study least square estimation, but often we use simplified formula, not the general case. But it's important in geodesy to study the general case. Usually we fit data with a linear model. Is a line, for instance, the linear trend in a time series. But in the GPS, we are going to see that if you remember, we started to say, okay, with GPS, we are going to measure the distance between satellite and receiver. So we have this quantity, x satellite minus x receivers square plus so this is our observation that we can obtain using code observation on phase observation. This is the measure. Okay. The coordinate of the satellite we can fix, we can know this, or we can also estimate. We can see different approach in the software. But at the moment, to simplify the problem, we say that we can fix because we have broadcast ephemerity or better precise ephemerity. And we want to estimate this quantity. But the relationship between the measure and the known parameter is not linear. So for this region, I want to show you the general description, formulation of the least square. Because it is not the simple case where you have a lot of data and you want to fit with a line, or also other case we have with a more different model, but always linear. Okay. Now we have a nonlinear relationship between observation and unknown parameter. So we started for the linear functional model, this one. Least square method started from two models. One is a functional model, that means a deterministic relationship between our observation and the parameters that model our observation. It means that if we consider a line, a straight line, we want to estimate A and B, the parameter of the linear regression. And another component that we take into account in the least square estimation is a stochastic model of the observation. We see Y are the observations, in this case D, or the double differences, and X are the unknown parameter vector. D are termed constant values, it's like B in the intercept in this case, simple case. And CYY is the covariance matrix of the observation, what we call the stochastic model. Or the stochastic model. This gives us information about the precision because we are using measure. So every measure can be a precision, an error, and the measure can be correlated each other. And we have to take into account for the precision and for the correlation. You know, if you have data with a big error bar and data with a smaller error bar, I want that my fit follow the measure with a smaller error. So this is important to know the stochastic model, because the errors, the uncertainty of the data are important for our estimate. Sigma, this is a priori variances of the observation. And the stochastic model can be written like a variance of the observation multiplied for the factor matrix. This Q matrix give you information about the relative weight between one observation to another observation. If this is 3 times than this error, for instance, and if there is correlation between these two observations, these are important. in a least square estimation or in any statistical method, also in a maximal likelihood estimation and so on. You have these two models, stochastic or functional model and stochastic model. Now we are going to see this because now we are in this case. We have our observation in terms of double differences, and we want just estimate, for instance, just the geometric parameters. We have a huge quantity of data because with the GPS, especially for permanent station or in a static survey model, survey way, where I put my GPS on monumentation and I wait for an hour before I switch off the instrument. We have a huge quantity of data because I can collect data every given second. I decide how many seconds. Also every 10 seconds or less. And we see a lot of satellites, so the quantity, the number of data is really high. So I give you just the formulation, not all the explanation. When you speak about estimator, you want that this estimator respects some condition related to the mean, to the bias, and you want that is a correct estimation and so on. Now we don't have time to, because we have to start a statistical course to give you all the definition. But now I just give you the notation. So you can, it's very easy, you can using this, you can implement this formula in MATLAB, but probably in MATLAB you have already, as you see, implemented code to perform this. It's not important, but I think that it's important to understand the basic concept. So, the vector of the parameters can be estimated computing this quantity. So I'm going to write on the blackboard the functional model just to remember. So we have observations that can be written as a design matrix. A is called design matrix, multiply for the unknown parameter plus the known term. So if you see, this is the estimator of the parameters, the formula that gives you a vector of unknown parameters. In this formula we have n. N is a normal matrix. Often in the program, practicing program, you see the normal system on the normal matrix, that is this quantity. And is a product between the design the transport of the design matrix multiply for the Q1, that means cofactor. Often Q minus 1 is called the weighted matrix. In Italian P, but in an English book with a W, as the weight of the observation. And A, this quantity is a n, and this is estimator. And the important things of the least square that we can have an estimation of the unknown parameter, but also of the precision of the parameter. Have you got any problem? We can stop. I have to wait 10 seconds to record. Okay. And so it's important that in this statistical estimation is not just to resolve an equation. You have the unknown parameters with the error associated to the estimate of this parameter. And this is really important because often it's important to know with which precision you can estimate a quantity. Not just not only the values of a parameter, but with which precision. Because sometimes you can realize that you can estimate, because it's a mathematical computation, a parameter, but this parameter has not statistical meaning, statistical significance, no, not meaning. It's not statistically significant. Oh, sorry. Probably the noise in your observation is too high, or probably the functional model is not so correct, or you have some big error in your data, outlier, what we call outlier. Do you know, big error in your data that usually before you to compute a known parameter, we reduce for outliers. Okay. So to compute the unknown, the covariance matrix of the unknown parameter, we need to compute a posterior variance that is given by this relationship. We have the different. Sorry, this is not equal. Is a 4. Is dot. I don't know why there is a equal. Is a mistake. Okay. Is all this relationship is over n number of observation minus number of parameter. I'm going to write to the blackboard to be sure. Sorry, there is a mistake. I'm going to check, to correct. So the a posterior variances is given by the number of observation minus the number of parameter. This quantity is also called degree of freedom. Okay. And okay, so you have to just to cancel these equal signs. So this quantity are the residual vector. In fact, you see the observation minus the estimation. No, it's working.
Is it working? Okay. I thought you stopped it.
No, no, the problem that sorry, I put the frame just slide, non slide più blackboard. It's too easy. It's too complicated for me. I have to speak it.
It's fine with slides only.
Okay. No, because there was a error, so I want to be sure that you have the correct formula. So I think that the problem was this. Yes, I didn't switch. Oh, it's complicated. And so this is called as the residual, because are the observation minus the estimated quantity. In fact, I use this symbol when you see the estimator of the parameters. I use this symbol above the vector, mean estimation. Okay. Is a convention. Is a convention. I don't know. It's not an international convention, but it's often used in the book that I use to where I study. They use this convention, and I think it's important to have an idea that this is estimation. What is an observation? So. Or an approximate values we are going to see. So what do you see that is an important, I don't remember if I put a slide, yes, Okay, you can see in this equation you have information about the design matrix, that mean about the relationship between parameters, the functional model of our the functional model, so the relationship that you think there is between observation and parameter. So I think that we have a linear regression or another more complicated, another type of function and so on. So this is important in a design matrix, but it's a design matrix. It's fixed. It's just taking into account of this relationship. And the other important information that we have, of course, the observations that are the core of the problem, but also the cofactor matrix or the weight matrix. So we put together functional and stochastic model to have a solution. But in this equation, you can see we don't use the a priori variancy. It's not important in the solution. We don't have. So it means that it's important the relative values between the precision from a point to another point and the correlation between points, but not the absolute values of the variance of in our data. It's important the relative weight. Okay, so if you have, for instance, black purpose, yes, Postgraduate. We became crazy. So, if you have, for instance, a covariance matrix given by, I try to do a good example, like we have seen before. Okay, this one. I can write this equation with this like 2, 1, 0.5, 0.5. If for some computation reason, for me is correct, yes. Yes. Is better to use this matrix instead of this. It could be happen because when you have big number, you have problem in the inversion of the matrix, and we need a Q-1, so we have to invert the matrix. So in this case, you can simplify the data because this quantity is not inside the formula, the estimator formula. Okay, so this is very simple. What are the important things? Are the definition of the matrix A, that is really important that I can cancel, erase. I see. Okay. It's important that A is a matrix given by if n is the number of observation, we have a matrix with n rows and the number of columns given by the number of parameters. Okay, if we have 1,000 observation, is mean 1,000 epoch, GPS epoch, we have 1,000 row, and the number of the column is the number of unknown parameters. The normal matrix is a matrix that has this dimension. Is given by is a square matrix given by the number of row a column is the number of parameter, unknown parameters. So I know that you know the regression case. When we want to estimate, we have this relationship. Sorry, time. So in this case, we are going to write A given by T1, 1, T2, 1, T3, 1, and so on. It depends on the number of observations. We have T1 because this is the coefficient of these unknown parameters. And we have 1 because this is the coefficient of this parameter, so it's always 1. The normal matrix in a regression case is a square matrix, 2 for 2, and okay, we have very simple. We have of course a number inside, but it's a square matrix 2 for 2. Okay, in this case the vector D is equal to 0. We don't have any constant. Okay, so these are the dimensions, and the covariance matrix of the observation, of course, is given by number of observations. Is a square matrix, symmetric. Also, n is a symmetric matrix. Okay. So the problem is the least square is to invert correctly the way as a cofactor matrix, and the normal matrix is you have a lot of data, but is a numerical problem is due to when you have a huge quantity of data could be a numerical instability in the software that compute inversion of a matrix. But now there is a lot of literature and already implemented codes to produce this inversion. So, is it clear? Usually, when I'm from physics, usually they give us the expression of A and B. Okay, if you have to fit a data with the lines, these are the two coefficients. Explanation about the minimum distance between the line and the observation, but you know the closed formula just for the estimate of A and B. Do you agree, Enrico? Or in Fisichetta is a course at Fisica? No, but you are not studying in Bologna.
We did the general case, but just theoretically.
Sorry?
We did the general case, but just theoretically.
Just theoretically, in fact. This is a really study in geomatics, because in geomatics is a surveying techniques. We also have a lot of quantity and the relationship, measures, and the relationship between the measures and the quantities that you want to estimate, the coordinate of point on the Earth, are not linear. You have a huge quantity, in the past not so huge, but you have a given number of observations. You have to really check if the network has been well designed to control in a good way the estimation, the parameter, and so on. So in the Faculty of Engineering in Italy, we study this part of statistics. In other faculty, no, for instance, we study just a simple case. Or we study, as Enrico told, the general case, but just for a theoretical point of view. So you didn't do exercise about okay. But now it's not a problem. We have all the software to compute this. We don't compute with our calculator of the data. Okay, have you got a question? No, you are arguing about something.
You said in normal matrix, D is 0. And
in this case, yes, no, this is a normal matrix. with given values. It is given by the product of A transport A multiplied for, okay, yes. In this case, we don't have any constant values. So the non, D is the sum of all the constant. Not the sum, it's a vector of the constant, sorry. Okay, remarks, some notes. When the cofactor matrix, I'm going to switch on slide on. Okay, when Q is equal to 1, you can interpret this estimation like as you have seen for the linear regression, minimizing the distance in terms of Euclidean distance between observation and the model, and this when you use as in this condition. Otherwise, in the general formulation, you are going to minimize this quadratic form. Okay, that give you is like a you have your observation. Okay, you want to find the vector, the theoretical vector of the observation that belong to the manifold of the possible values that we can have. And this vector has to be more close to the observation. More close is so you need to have a metric to measure what is mean close. Do you understand? So in least square we use as a metric a quadratic form like this. Sorry, we put P, but in this case with Q. Okay, is under the. In fact, I put P here. Okay. Okay, just to say, the principle is always the same that probably you already studied in your previous course, but it's a more general. Okay. Of course, I give you in this slide some information about variance covariant propagation law. We have seen when we have talked about the noise in the data due to the differences between observation, and also in the just a moment. Okay. Now, sorry, because I don't know why. Sorry, I have to check. So I put the definition of the variance covariant propagation law in using. In the linear case, when if you know the covariant matrix of this quantity x, you can compute, and this quantity is related to the quantity y through a linear relationship, you can obtain the covariant matrix of this quantity using this relationship. Okay, so I mean. Probably you know, I'm going to write an example. So, supposing that you have epsilon given by APB, and you know the variance of A and the variance of B, you know what is the variance of y, which is no, sorry. You know, but you don't want to answer me because it's a trial question, no? No. Okay. So we have done an example, so now I think that the blackboard will be recorded so you can see. Now is an important case what you have in a nonlinear case. In this case, it's like if you linearize the relationship, so you have a general function between y and x. So it's like you linearize this relationship. So you obtain more or less the same formulation, but it's an approximation because it depends on the Taylor expansion of your function, computed in the mean value. Sorry, this mean, I probably didn't write, you can add in your notes. This term, the Greek letter, means mean values, average values of x. Okay, is a mean. Or if you want to, if you know that the relationship between some quantity epsilon y given by I don't know, exponential of the time square, for instance, and you want, and you know, no, sorry, and for instance, and you know the parameter a, and you know also the variances of the parameter a, you want to estimate the values of y, sorry, at t equal to 5. You put here 5, and the mean values, in this case, you know, this here, mean that is the meaning of this one. Okay. So, I propose you an exercise. Okay, we are going to see is not to calculate now. I give you a homework, so you have a long weekend. Sorry to do. I'm sorry because I think that on Sunday and Saturday you can have a break and go around for Trieste, for Italy, and so on. But we have a lesson on Monday, so you have to work tonight or during the weekend. I'm sorry, it's not depend on. It depends on the schedule of the lesson. So, and this is an exercise. We already done this with a linear regression, but it give you an idea how to define this type of problem. So, a bacteria population follow a law of creation of this type. This is the bacteria population, the number of bacteria. Given the measure reported in the table, I just 3 measures to simplify the computation, of course. Estimate the parameter B and C and the corresponding root mean square using the least square estimation method, supposing that the observations are independent and with the same precision. So from this we are going to see. Okay, this is, we can write 3 equations to different time of this. We have in the case, oh sorry, I put D, this is the general form. Okay, to be honest, the general form of the linear model least square is given by this one. I can also add a matrix that multiplies the observation, but at the moment, in this case, T is equal to the identity matrix. Sorry. So D is equal to 1. We not multiply our observation for something. And these are our observations. We have to write the design matrix. We have seen that we have to put the coefficients of the unknown parameters. So before the parameter B, we have 1. and before the parameter c, we have the exponential at the given time. Okay, this is an unknown parameter, and this is the unknown. And I don't know why there is this, probably. Probably I cancel the fact that Q is equal to the identity matrix. No, yes. This is the reason of this note, because I think that for some reason I remove one equation. Q is equal 1 because the observations are independent and with equal precision. So we don't need to know which is the precision, because this precision could be the a priori variance, the sigma 0 square. And we have seen that in the equation of the estimator of the x vector, we don't need to know really these values to obtain the results. So you can do all this computation and find it's very simple. Just when you compute, you can check if the n matrix, normal matrix, is really a symmetric matrix. Yeah, so you are sure. You know that it should be a symmetric matrix. So if you, sometime when you are writing code, please check if what the matrices that have to be symmetric are symmetric or not. Okay, just to do not have problem in the inversion. Okay, and so the important core I want to show you before the break that is very important. You can also have a code to compute all this matrix computation. It's not difficult. The only numerical problem that you can have is in the inversion of the matrix. But it's really important that you can write the design matrix, and you write the design matrix, because I can write a general least square estimation code in any languages, but I have to put in the data, so I have to be able to write the design matrix and also, the stochastic matrix. I need, the software needs these two conditions, these two information, and we have to be present to know how to write a design matrix. Each row is related to a parameter. I cannot mix. I have to be to sort our observation. We cannot change the order of parameter row for row. No, we have to. You need to have a column for a parameter, another column for the other parameters. So this is our task. After you can use a different code. Okay, I give you a homework, so it's very easy. You can with the Excel or with the MATLAB also. I think that you can put with MATLAB or Octave. I don't know if you have MATLAB on your laptop. I think that from ICTP you can install MATLAB in your server version, I suppose, of the MATLAB. Or you can download Octave. Octave is a free version of MATLAB. There are some little differences, but for this very basic computation, you can use the same code, the same command. Sorry. So please, do you have this? You can do this least square. It's very easy. You have to estimate A, B, C is a linear problem, so you don't have any. I think that you don't have any problem. Okay, we can have a break.